Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. So back to making videos and, such. A little more work for me, actually. Yes, we'll avoid the distraction of the endless and perpetual drivel of the average commenter. Frankly. So, I mean, it was a learning experience. So for a couple of months, I learned that people are really, really, really dumb. I mean, I thought they were a little bit dim, but I didn't think people were quite as dumb as they are. And it does explain a lot, frankly, what you see walking the streets. So it just makes the job that much harder. I guess I will maybe even look on eBay and see if I can get a Barney the dinosaur suit, when we can all talk like little babies and little kids because you can't understand any concepts at all. But whatever. We'll see if I go that far and trying to indulge your profound ignorance. So, and I'm talking about the physicists, frankly. They're really stupid. This isn't that complicated. Okay, so the Gostling guy has, he made a couple of, it was a nice vacation. I didn't bother looking for a few days. He's made a couple more moronic videos. So, we'll play them and show how, they're just, they're sort of, okay, they're intelligence tests in the sense that he's done something to fuck something up, and then I have to figure out what's fucked up, right? So it's like they put a, a street light inside, one of the apples on the tree is a street light, and you have to, there's a street light in your tree, I have to find out where he's broken the rules. Just too stupid. Alright, so I'm arguing, that the universe is this consistent thing, three-dimensional space, stuff moves into space, things actually have to give their energy to something else, so they have contact with each other, and it doesn't matter which one's actually moving, in a sense, but it just means they're going to share their condition when they interact with each other, depending on how long they stay connected. They now have the opportunity to, for penness to get into, Clipper. And the two things now can interact and give each other its condition, share their condition, and then they can leave. So in some cases, all the condition, all the apparent movement can go into something, or some portions of it, but it always has to be conserved, that there's only so much of this stuff called movement in the universe, and the movement you can always just follow it. There's a certain amount of it, and it's conserved by the universe. Nothing moves without being hit by something that's moving. That's the simple argument. Photons moving, it hits something, it gives it some pressure, and it will continue, the photon energy will continue to be revealed in movement. It's probably not the best example just because photons don't exchange it. The photon either is absorbed, that is, it sticks to the object and keeps pushing it, or it reflects, but there's no sharing. Photons really don't share. They impose. They possess something. And that's probably a good way to think of energy, is just little tiny bits of stuff moving, and you either have some of them or you don't. In a way, you either have an imbalance of them anyway, you could argue. You have a certain amount of these little bits, and the bits are, like a school of fish, as I probably analogized it to that 10 years ago. And it's just, you can have fish going in all kinds of different directions, but the fact is you have to have, for the whole school to move, more fish have to be going this way than going that way. And that's all you need, is to have more force bits stuck to you that are going this way instead of that way, and then you'll move. Alright. Okay, so it's a little bit of the basics. Alright, so gravity. It's I guess I'll draw this part one more time. So I would like them to do what I'm doing, which is explain how they think this force manifests. And they won't do that. Instead, they'll do these silly little gimmicks of unknown purpose. I mean, they're not very functional, not very analogistic to actual reality. So, as I have attempted to point out, to clarify the position, to make it more exact and precise. Okay, I mean, it's one thing for me to say it's a time-dependent force, I suppose, but I should explain that what Newton discovered is that it's 9.8 meters per second, per 1 second, okay, of time. So in 1 second of time, this happens. That's the ratio. Okay, so they draw it all kinds of ways, but I'm just saying that's the ratio. All right, now the ratio could be just as validly stated as being 4.9, okay, meters per half second. That's just as valid, okay. And obviously you could do the 19.6 per 2 seconds. Okay, all of those would be just as valid. Newton could have said this, and it would have been just as valid. Now everybody would have just said, well, why don't you make it simpler and put a 1 there instead? Because then we can forget the 1 exists. See, that's the catch. See, the catch is if you have a 1, everybody just says, well, the seconds already says 1. You can't have 0 seconds. So the 1's already there. It's already implied. See, they say it's already implied. But that's the gimmick, right? Because then they can pretend it doesn't actually exist, that there isn't a certain number of seconds that the 9.8 happens in, and that if you change the number of seconds, you change how much force there is. All right, now the obvious implication of this is this exact thing, that you can see that the force doubles, okay, as the time doubles. It's not a 4-to-1 relationship. It's clearly a 2-to-1. Okay, that's what it is. All right, clear, 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 clear. In the sense that the double is a. Well, why am I saying it's a 2-to-1? Yeah, no, that was a mistake. Too bad. I am not going to edit that out. It just means a 2-to-2, 3-to-3. It's a 1-to-1. 1 second gets you 9.8. That's the rule. That's the ratio. And that's it. Okay, and this is acceleration. Okay, but it doesn't really matter. You can call an acceleration, you're going 30 miles an hour, and then you change, and now you're going 60 miles an hour. All that is a change. There's a little period in here where you got a little boost, you got more stuff. And so you have more stuff. I could make it weight, right? You could be 30 pounds and now you're 60 pounds. Well, what did I do? I just added the extra weight. I didn't do anything special. It's a certain amount of weight. This is the thing you're adding, okay, to your velocity, 9.8 every second. It's not incredibly special, okay. Clearly it's something that lasts. When I give you the extra 30 pounds, you're not losing it. So if you get another 30 pounds, then you're up to 90 pounds. And your weight doesn't undo. Okay, your velocity doesn't undo. So once you get this extra velocity, every second you're going to be going this faster and faster speed. So in the first second, you only travel 4.9. Okay, but you're moving, your velocity is now 9.8. Okay, so in the next second, obviously you're doing the 9.8 thing, which is 2 units of 4.9, you can understand. And then you're going to get a third unit of 4.9, right? In the second, what's going to happen? You're going to get another 4.9. You're not going to get something else. You're just going to get the same amount you got here, 4.9. You got 4.9 distance in the first second. You're going to get 4.9 distance in the second. That's the only part the new gravity is going to give you, the new second. The new second is here, second number 2. This is all it gives you, 4.9. In the first second, all it gave you was 4.9. Okay, this is your accrued velocity. Okay, this you don't have to do again, these two 4.9s here, sorry. I don't want to imply the whole thing is 4.9. This 4.9 and this 4.9 are a consequence of the 9.8. The 9.8 gave you this. Let's see how to draw that. This whole part, okay, was because of this 9.8. You didn't have to do that again. You already got it as a velocity. So it's giving you 4.9 each time. So even though I do this again, I could go all the way down here, 3, 5, you know, all the odd numbers, 3, 5, 7. The part you got from your already captured part gets bigger and bigger and bigger, and the new part is always just 4.9 meters. That's all you get in extra distance from the new gravity you are getting, the new boost. The new boost in your velocity just gives you this 4.9 each time. And it's just kind of obvious that, frankly, it's only 2 units of force. You've only gotten 2 units of acceleration. You can't say you're going 150 miles an hour. No, you only got 2 units of acceleration. That's all, just the 2 units of it. 2 units of force. And this is called force. Okay, it's not called something else. It's a force. And as Newton said, the force does equal the energy. So all you have to do, you want to go twice as fast, then you just add twice the force. Force equals, it equals your momentum. It essentially will equal your velocity in these cases where you're not going to change the mass. So if you're not going to change the mass, the increase in the force will be proportional to the velocity increase. That's it. It's a one-to-one thing. Okay, 1 unit of force. Oh, I should just say force equals energy. Okay, quite obviously in this case. So, you know, that's you don't need to make it complicated. You can't have, it's not for every you know, 4 units of force you get 2 units of energy, and it's certainly not every 2 units of force get 4 energy. I can't have 4 units of energy if I only got 2 units of force, and that's all I get when I drop from 4 times the height. If I have something that just does this part 1 second, and then I let something drop for 2 seconds, the comparison between those two things, okay, has to be fairly understood, that this whole section in the middle, this middle part, this was for free. And this is what the force is doing. So it's only 2 units of force. Yes, you got 4 units of distance, but those weren't energy distances. Those weren't distances for which you had to have new energy to travel. Those were residual energy. That was already the consequence of the 1 unit. So yeah, so there's a slight illusion here in the sense you're seeing 4 times the distance, but you can understand, oh, you're traveling really, really fast, so you're going through the gravity. All right, so we'll do the rain analogy, where they don't argue in any way. Does anybody explain why it can't be? Okay, that gravity's a push force, and that it's pushing just as if it was an invisible rain that we couldn't see, and the invisible rain collected on an object based on how much mass it had. That's the stickiness. The little matter bits are the sticky part. The force sticks to the little matter bits, so the more matter bits you have, the more force that'll stick to you, and you'll be traveling. Your matter bits will be able to travel the speed, and that each fish has to be hit. The school can't move in a direction if all the fish aren't motivated to move in the direction. They all have to be forced to do it by something. All right, so this is the simple visual. It's just, apparently it's just too much, for the viewer, the casual viewer. They just can't imagine how, well, this can't be a 1-to-2 relationship in terms of the interaction, because this is 4 times the distance. So how can this only have twice as much of something? But again, if you understand that the force is actually, something that's coming down and it's hitting the object and pushing it, well, then you could understand it, because you can understand how, yes, as it's pushing, it's going faster, and it'll be getting pushed less time. So you're really talking about how long does it take to get from one location, a point A, to a point B. And you're just doing the simple logic that, well, the amount of time it takes depends on how fast you're going. And if you go twice as fast, okay, if you go twice as fast from point A to point B, you'll only be in it, you know, a quarter of the time, because your speed will be parallel to how much distance you're able to travel in a piece of time. So this will just be 2 seconds, and this will just be 1 second. And the time is telling you how much time does this stuff hit you. So you're in front of, let's just say, I've used the paint sprayer as an example, but you're going to go past a paint sprayer. You can certainly understand the faster you go past the paint sprayer, the less paint that's going to get on you. So there's just no way somebody could miss that one, right? That one is so in everyone's experience. So you can understand that the faster I move, if there was a paint spray and I move my hand really, really as fast as I can, I'm going to get very little paint on my hand. I move my hand really slowly, I'm going to get a lot of paint on my hand. So we're just talking about how long you're in the gravity. It just depends on how fast you're going. Your speed will change how much force you can collect. So you know, it's just that kind of obvious. So we know that you collect just as much paint, okay, in this 1/4 distance, because the paint's hitting you. Okay, just imagine they're both in the same position. So, you know, we're just doing this 1 little quarter of the distance, and the paint spraying in this 1 unit of time. Okay, and this is the second. You can understand that in that 1 second you got just as much paint as you got in this whole section, because it's really just about how long you're in the paint, and this is how long you'll be in the paint. There'll be this 1 to 3 relationship in terms of total amount of distance, but it's a 1 to 1 relationship in terms of time, and that's the key thing. The time will tell how much paint you get. The distance doesn't tell. The time tells. So it really isn't that hard to figure out, right? If you're going faster and faster and faster, this section you do in the same amount of time you do this little section, you're going to get more paint on you, the same amount of paint here as you got through this whole big long distance, because it's about how much time your hand, your whatever, anything, is in the force, is in the thing causing the effect. How long, how much exposure do you have to the bent space, if you want to call it that? Okay, it doesn't matter what you call it. It functions by the inverse square rule, which is the same rule by which the paint sprayer is functioning. So it's a perfectly valid analogy for even bent space. It just doesn't matter, because the only thing that's really important is that it's a constant amount of stuff, and you can change how much you'll be affected by the stuff by getting through the field of the stuff at a faster speed. Less exposure to the stuff, less effect of the stuff. Now this same rule goes for when the spray is coming down. Okay, so that'll probably confuse some people, right? They'll just totally not get it, because why wouldn't it draw up and down? Huh, it's interesting. Anyway, so the force is coming down, and you're going to go the same way as the spray. I mean, it's the same. It's really the same experiment. You're not really going to be outrunning the paint particles, because they're moving much faster than you. So you're not. It's not a matter of outrunning it. It's just a matter of how much time are you in it. And that's all that's going to matter. It's going the speed of light in the case of gravity, and you're going 1,000,000 times slower, or 100 million times slower. So it's not going to have any effect on how much paint hits you. Alright, so I have, simply explained, gravity and the speed argument by just drawing a simple diagram where you have a planet, the Earth, or this could be the Sun, and this is going to be the Earth and the path it takes. Now, obviously, the Earth going around the Sun, it doesn't travel the straight line, but the fact is we can understand that if we just slowed it down or sped it up, we could make it a straight line. So it's not really a problem. Okay, so it's in an orbit, and so the orbit is a certain distance, and the fact is we can bend it or we can not bend it in terms of bending the line that it wishes to travel. So you could make the simple experiment more complicated by playing a game, but the point is there's going to be a certain amount of light. If it was the sun, there's a certain number of photons that are going to be in this field. This field you're traveling through, this portion of the radiation coming off the sun. Okay, say if the sun was way up, we're just going to say there's a certain amount of pushing radiation that's going to push you. And that's the same thing as gravity, same inverse square law. So again, it's back to the paint analogy, or any analogy with a constant force coming from a point source and radiating outward. You'll get the same effect. But the simple point is this field is a set amount of exposure to whatever the gravitational phenomenon is. Yes, it's a little weaker here than here in the center, but you can certainly understand that there's an average density. And what you're going to do is just travel from the point A to the point B, okay, through that field, and all that's really going to matter in terms of how much you're going to get bent by the pressure is how long were you in it. So the faster you go through the gravitational field, okay, the less and less you get bent, and the slower you go through the field, the more and more you get pushed into the center that's creating where all the stuff goes to die, so to speak. All the little paint particles are heading. I mean, it's a simple, kind of obvious concept, completely understandable. I mean, even if I drew it as the surface of the Earth and I made the surface apparently flat, you could sort of understand that a speeding bullet, okay, can go further before gravity collapses it, right? So if I shoot the bullet very slowly, 50 miles an hour, okay, the bullet just goes bloop and hits the ground. I do it 100 miles an hour, then it goes, and then 150, and I just keep increasing how fast I'm going. I'll keep increasing how far it goes, even though it's the same force pushing it down. The fact is, it's the amount of time. This time will always be the same. The time it takes for it to hit the ground will always be the same, no matter how fast I shoot it. This time will always be the same, 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 always be the same. And what am I doing? I'm getting huge amounts of distance in the same amount of time. And so it's the same gravity pushing down, and you just have to use the same, let's say if it was just 1 second to do this, you just have to extend the second in terms of distance, but the time it hits the ground will be the same. It's not going to change any, because yes, it's going down at a fixed rate, and all you're doing is creating more distance by creating more velocity. The whole experiment happens faster in the sense of you're going this whole distance in the same 1 second. This is 1 second, this was 1 second. It's the same amount of time, same amount of pushing force down, same impact with the ground, because they all, there's no difference. This distance doesn't mean anything. The only thing that means anything from the forces perspective is this. Alright, and this part, okay, again, it'll look like a lot more bending here than it'll look like here. Alright, and obviously because the world is round, the bullet will eventually just fly off the surface of the Earth and go into space. Alright, if you can go fast enough. So that's the background. He's not going to draw a competing drawing explaining how there's some other truth. And instead he's doing this, whatever, the theater. This theater.
Right, if this is a planet,
I guess we're going to need more volume. So that's a planet.
and if my fist is a spacecraft and it's flying past the planet,
Right, and there's a constant spray painting force. There's a force back where we are, the viewer, and the force is spewing paint particles at the object. That's the simple analogy.
We're moving from outside the gravitational influence to within it.
Well, we're really not. The gravitational influence is getting, the density of the force is getting increased because you're getting closer and closer to the object where the force is ending. So it's like being closer and closer to the light bulb. More photons will hit you. Now gravity is the inverse in the sense the force is going towards the middle of the object, so it's the same effect though. Same inverse square law for stuff going out as it is for stuff going in.
So then past it again. But obviously, the faster you move past in your spaceship, the less time gravity's got to affect you, isn't it?
Okay, so why are you arguing? It's a completely time-dependent force. You can't collect the force unless you're in the force. It's how long you're in the field that contains the force. The less time you spend in the field that contains the force, the less force that can affect you. So I don't know how you screw this up, but you're going to screw it up. Because that's all you people do is screw shit up. Sorry.
You can see that. But how would this apply to the Earth? Because we're in the gravitational force constantly. We're not.
Yes, so it's the same. The Earth to the Sun is exactly the same as the Earth to us. There's no difference. The rules aren't any different. There's no reason to say how would this apply. We already know how it applies. We're experiencing it right now.
Moving from outside of it to in it to out of it again. We're not moving past it. We're in it. We can't.
Of course we are. So he doesn't get this simple concept. Let's say you're going across this much surface. There's gravity coming down on this much surface. Okay, I can't get all the gravity going over here, and the gravity over here isn't in here. The rain is a constant force. It's a constant amount of rain per inch on the surface. Okay, you could just say that's how much gravity there is. Okay, a 10-pound weight weighs 10 pounds no matter where I put it on the surface. Okay, it always weighs 10 pounds, and it's only 10 pounds for a certain amount of surface area. And that's all. Okay, so you can't change the rate of the gravity per a certain unit of distance. And so obviously if you travel across that distance faster and you haven't changed how much rain is falling, you're going to hit less rain per that distance. If I had to travel twice the distance at the same speed, twice the rain would hit me. I mean, really, you really have to go all the way back to kindergarten.
Tape it. So I can't see how this example Gary uses can have any influence on anything that happens on the surface of the Earth.
Obviously what I'm saying doesn't have an influence. I'm describing what happens on the surface of the Earth and anywhere else. I just showed the example of the bullet. The bullet's going faster and faster. What is it doing when it's going faster and faster? Well, it's evading getting hit by the rain the same amount because it's not in it long enough. And only by going a very long distance does it get hit by the same amount of rain. It takes a very long distance before it has been hit down the same amount. And what decides how much it gets hit will clearly be the time. As soon as it's the same amount of time, that's when it hits the ground. When it's accomplished the same time in the force, then it got the same amount of force. I mean, it's not that complicated.
At all. I don't see it.
Alright, so he doesn't see it. So no matter how simple you make the diagram, I mean, I really think a 10-year-old could handle it. I mean, I really think that a 10-year-old could understand if it goes outside in the rain with a bucket, okay, and he's going to run from point A to point B, and he runs at different speeds from point A to point B in the rain, that he's going to collect different amounts of rain. You know, and that if he runs in circles, it won't matter if he takes the same amount of time in the rain. It doesn't matter whether he goes circles, doesn't matter which way he goes. It just matters how much time he's out in the rain field. The amount of time in the rain field will decide how much rain gets in his bucket. So I really think a 10-year-old could handle this, you know, without much trouble, and say, yeah, that fits, and it certainly fits all of the you know, you're not going to go through all the details with a 10-year-old, but I'm just saying it certainly fits all the experimental data regarding how things behave, satellites and moons and objects in space. All you have to do is calculate how much gravity they're in, what's the field strength, and then just figure out how long they're in that field strength. And once you know those two numbers, you're all done.
That's the first thing.
Alright, so now he does this lever stuff again. I guess this volume is still kind of low. I suppose I'll speed this up because, again, it's like all his other videos. He shows you something and then he just kind of grinds it in. It just says, look, 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 look. It doesn't work, it doesn't work, it doesn't work. And so, he, you know, again, this is just a little puzzle he set up for why, you know, I have to explain what kind of gimmick he has done, what kind of way he broke the experiment. And now I have to explain. So I have previously explained that, you know, consistent quick releases are always a good idea. Now, he doesn't think that's important, and so that's okay. I mean, in this case, it might not be, but it's a good rule of thumb. Okay. Now, the argument about levers is that clearly the scales that we see, like if we put scale into Google, especially like medieval scale or something, they'll either put the weight on top of the balanced rod or they put the weight below, suspended, hanging, because it makes it more accurate. The fact is that the tension on the lever is more precise because the weight is dangling, which means all of the force goes straight through the little suspending wires or chains, and it doesn't matter what position it's in. You can't change its weight by changing through angular movements. An angular movement won't change the pressure down. The pressure, the weight will always stay in one direction, and you won't change it by causing a conflict with the angular motion. The motion sideways won't interfere in any way with the constancy of the weight. So I would say it's a good rule of thumb. That would be my argument. But that's not the flaw here. Okay? I mean, it's a flaw, I would argue, but it's not the flaw that's deciding why, okay, he's again created a rigged experiment. Okay? He's engineered the experiment to fit his conclusions. And he's just really saying, here's a test. Go figure out what I did wrong, okay, to make it come out my way. And that's all this is. So I'll explain. I mean, it's obvious, okay? They're always obvious. I mean, you should say, okay, well, these are zip ties. So he's tied the lever to a bearing. Ooh, wait a minute. Why isn't the bearing in the middle of the lever? See, that's something you could say to yourself. Now, that wasn't the first thing I saw, but it was something I saw, and I did see, oh, that's a little curious. But I really didn't think of the implications of it right away.
Balanced, oscillating levers.
Now, you know, he shouldn't just do this herky-jerky stuff, right? Because he's showing them not in sequence, right? And they're supposed to be oscillating exactly the same. The same energy should cause the same oscillation. So he shouldn't really have done that because he's basically showing that he can give them a different oscillating rate. Simple enough.
Because they are balanced with ball bearings to reduce the friction.
Okay, so he's pointing right at the ball bearing, right? And this is the fulcrum. And guess what? It's not. It's not in the center of the lever. So I mean, he's made such a, you know, it's a, you know, we all can all make mistakes. I mean, I'm not saying you can't make a mistake, you know, in terms of not seeing something where you've sort of broken the experiment. So I'm not saying he's, you know, deliberately knows that this is not, you're not allowed to make this mistake. Okay, you know, it breaks the experiment in a critical way. And he, you know, he just didn't notice. Okay. But I'm just saying it still doesn't change what he's doing, which is I'll do the experiment all kinds of different ways until I force it to come out the way I want it to. And he's just going to keep throwing those kind of experiments at me and saying, show where I made a mistake, show where I made a mistake, show where I made a mistake, show where I'm, you know. I don't know whether that's at all productive, but whatever. So what he's done, you know, is made a gear. All right, and this is the center. Here's the fulcrum. And he's tied the lever, okay, here. So now the lever, okay, you could almost think of it as just being on a pendulum. So he's taken the whole lever and essentially put it on a pendulum, and now he's going to swing the whole lever. Like the lever will be in this position, and the lever will be in this position. Here's the fulcrum. Here's the fulcrum. So he's moving the fulcrum of the lever. Wow. Have to remember the details, Gary. Have to remember the details. I'm getting a little better at remembering, but... Alright, so instead of having a lever the way it should be, which is, okay, you just have the bar and you have a fulcrum right there in the middle of the lever. That's the R. You put a little triangle here and you let gravity create your pivot point. Or you suspend the lever from a wire to a little spot in the center there. So the center of the lever isn't going anywhere, isn't doing anything. And especially when you're putting the energy in. See, when he's putting the energy in, what is he really doing? Is he's taking something balanced by gravity, and he's going to move more mass on this side of the bearing. So this side, when he pulls this up, what he's really going to be doing is taking 3/4 of the mass of the lever and picking it up and putting it over on this side. So he's obviously moving the whole mass over. And in this case, there's two versions of the lever. One version weighs, okay, more than the other version. One version has 4, you know, 2, a 2. The other version has a 2 and a 1. So it actually has less mass. So this version has less mass. He's lifting less mass here than here. So when he lifts them both up and has them in this configuration, one of them has a little bit more mass, and so now it's going to swing down, and this one's going to end up having less momentum. There's obviously less force going into the oscillator because he took less mass and he lifted it the same distance and dropped it. And although they'll just fall at the same speed, what they won't do is have the same impact momentum. And in this case, we're not just dropping something, we're oscillating, which means we're shifting, okay, the force from one side to the other. And so this one will have less momentum, and that's why it will oscillate at a slower speed, is because it has less momentum. So it can't oscillate at the same speed because you put less energy in, because you put less gravitational weight. This one had more gravitational weight. This one was a little short. It didn't have this part. You took one piece of the actual mass off. You reduce the actual mass, and therefore you have less mass in the gravity. You're letting less mass fall, which means you have less energy in the system. So this one was given less push because there was less gravity collected, because the total object has less gravitational mass. I mean, it's a subtlety, but I think anybody can understand when you look at it. That's the wrong way to do the experiment. That the fulcrum, okay, all of the movement has to happen through this one little tiny space. And if I move the whole fulcrum, what am I really doing is I'm lifting the whole lever now. All right. Not too hard to catch or understand.
Plastic tubes, quite light, distributed weights.
So this is the other part where if you really thought about the experiment some, you'd say, do I really want to have to make a fixed, drill a hole? wouldn't it be better if I could just slide the weights? You know, I had some way where I could move them little tiny subtle distances to see how it would change what happens. So in the case of this experiment, you could imagine that, yeah, if I just change where these weights are located a little bit, I probably can fix the broken oscillator. In the sense, I can probably make the two oscillations match. But he doesn't provide that option because he's doing it his way.
Because of the bolts to hang weights on, but the ratio of the mass of the...
See, I use magnets, okay, because the magnets I could put in any position and they dangled down below, and so it was kind of a really useful way to do it because you can change anything, you know, and start over and do it differently. Very variable. It's very adaptable. This is very unadaptable. Now, he certainly could just hang his weights from these little pins, and that would be better than him consisting on putting the weights in the plane of the lever, which does in fact create a difference. Now, I don't know how much of a difference it is, but it's always better. The scale will be more accurate if you can make it more precise where the weight actually is. And you do that by dangling the weight.
Won't affect the experiment we're doing. If we're putting weights on at different points, these weights of the bolts are effectively become the distributed mass of the lever, and they're equal. So as long as they stay in place, it makes no difference to the experiment. And I'm going to leave them there.
I don't know if it makes no difference, and I don't know if these are perfectly balanced either, but whatever. Go ahead.
We want to see roughly, when it's given an impulse, the impulse is gravity, that they accelerate roughly together, which they do. It will drift over time.
Well, it's not drifting over time. It's the fact is that there are changes that you're creating by not having a consistent release mechanism, probably more than anything else. And obviously the total weight of the two levers could be a little bit different. But again, the real point to watch is this is not a fulcrum. The fulcrum is not, okay, in the center of the lever. He's swinging the entire lever like a pendulum. I mean, you could extend that with a steel bar, and you could even understand even more just how eccentric that is. He's moving the whole lever back and forth. The fulcrum's going from this position to this position to this position to this position. He's moving the fulcrum of the lever, which you're not supposed to do. The bearing, he should have glued, or however he wants to attach. He should have just made a single, you know, obviously if you're going to use a bearing, the bearing has to be in the center of the mass of the lever. If it's outside the center of the mass of the lever, then you're going to be rotating the mass of the whole lever. You're not going to be comparing side A to side B anymore.
We're not interested in time. It's only the first oscillation.
So he says so. So he's just saying that, like, oh yeah, it's only the first oscillation. No, any irregularity created has to be created out of something's energy. You have to explain why one of them retains that energy and one of them doesn't retain the energy. All those things are worth explanation. Now, clearly, I can see it's not nearly as much of a distortion, so it's not a big deal. It's probably not affecting the experiment any, the minor bit of energy differential you've put into the two objects.
That's the accelerating period. Do they accelerate together? And they do. Nicely. Good enough, anyway.
He keeps making declarations. Like I said, I'm not going to agree with those declarations. Good enough anyway. Okay, yes, all right, I'll concede, but obviously it would be better if you made it perfect. More perfect.
Now then, to test whether changing the distribution of weights affects force required.
So let's just understand. See, he's testing it with no weight on it, right? So you could understand that sometimes you can change something and it magnifies an effect. So he showed us that there is a little defect, and now he's going to put more mass on. And the the argument would be is that this will be a case where the more mass you put on, the more any defect that exists will end up showing, because all the stresses will be increased and all of that. And so, you know, it really just depends on which way you're going on a system. Some systems you get rid of the imbalance by adding more weight. In other systems, you make the imbalance more, you make it more sensitive to the imbalance. And I would argue in this case, adding more weight will be more revealing of any imperfection in your balances. So you could argue that the weight multiplies the defect he concedes exists, but says it doesn't matter.
We've got to put some weights on. And here we have some weights. They're doubled up because I'm going to split one and move it to the end, you'll see.
Alright, so again, he's got them in line with the lever, which, as pointed out in previous videos, probably isn't ideal. And you can see when he puts them on, they're a little square. They're different shapes, and he has them oriented in different configurations, which also probably is a long way from ideal. A long way from ideal. I mean, depending on which way he puts this weight, there'll be more mass above the lever than below the lever. That's not ideal either. That's the same thing as messing up the fulcrum, is if you have weight distributed unevenly above and below.
Right. Balanced again.
Well, not quite, right? So, I mean, it was kind of obvious that it wasn't quite balanced. Okay, one of them was a little bit out of alignment with the other one. Just a fact, so, you know. So.
Much, glad to say. They oscillate together in unison or synchronicity. What lovely words.
Whatever. So, yes, and that's good. And he's also not pushing them too high, so he's keeping the amount of energy he puts in to a minimum. Well, it's not a minimum, but it's not a maximum.
Good enough. Now, what difference will it make if I put half the mass there?
So what he doesn't do is what he did in the other experiment, which is put the half mass on the other lever. But again, all of those details, right? All of the things I'm complained about in the past, he won't fix those things, and he also made this is the critical error. Okay, so you can just understand this fulcrum, here's the fulcrum. It's way above the center of the lever. So all he's really doing is, again, every time he goes this way, there's more lever on this side of the fulcrum. Total lever. There's more lever on this side. More lever. You get it? There's more. Oh, you can't get it because I don't have it on. Alright, so all that was a lot of, well, there wasn't much for you to see, frankly. But we'll play it. And you can see this, the bearing is here, above the lever. And so when the lever's oscillating, it's essentially a pendulum. And all the mass ends up going on this side, and then the mass ends up going on that side, and then the mass ends up going on that side. You're not supposed to be changing the locations of the masses. So you can't hang the lever from a fulcrum. You have to have the energy. The fulcrum has to stay in one place. It can't be swung back and forth. That's not even the right way to say it, because frankly you can allow the lever to oscillate this way, but you obviously can't allow it to put more mass on one side of the fulcrum and then put more mass on the other side of the fulcrum. That won't work.
On the end, I'll split it in half so it still balances. Double the distance. What difference? It shouldn't make any difference according to Gary.
No, it wouldn't make any difference, but the fact is that one lever now has less mass. So we understand that this lever only has 3, the other lever has 4 masses. So obviously if I'm going to use gravity as the source of the force you're going to put into the lever, I can't collect as much force with the smaller total mass. So less force goes into the one lever than the other. The one with only 3 objects will move slower because it doesn't have a choice. It can't create the full momentum, the movement, because it doesn't have the energy to do it. there's less energy in the oscillator because there's less total mass. And it's because you put the force in by lifting the entire lever to one side. By imbalancing the lever, you ended up putting, you ended up making the masses relevant instead of the weights. If you want to just compare the weights, you have to move this fulcrum to the center.
The same force will produce the same speed of oscillation, the same acceleration of this lever.
Yes, it would.
Breaking the conservation of energy, because this one will be moving at twice the velocity now, because it's twice.
All right, so let's also understand, it's like he's denying what the experiment I did, okay, where it perfectly does oscillate. I mean, I don't think I should have to replay that video, or even, you know, the lever's hanging right over there. I could take a picture of it. I mean, I could videotape the lever perfectly oscillating with a quarter mass out here, 4 units of distance, and a 1 mass here, and perfectly, I mean, 4 masses, four objects hanging here, 1 object way out here, 4 units of distance, and it oscillates perfectly. This moving 4 times the velocity of this. Oscillates perfectly. So he's almost arguing as if that doesn't happen. I'm saying, if you can't agree with that, then there's really no point in having any further interaction, because that's just so elemental and so well understood. I mean, it's how scales work. It's how scales in doctors' offices, you know, the ones where you move the weights, the sliding weights, it's how they work. I really shouldn't have to go through a bunch of work to defend that theory. So the fact that the oscillator has, in fact, okay, more velocity and less mass on one side, but the same momentum on both sides, and not the same kinetic energy. One side has 4 times less kinetic energy in the 4-to-1 relationship. It's 4 times less kinetic energy. The 4 mass has 4 times less kinetic energy in the oscillator than the 1 mass moving the 4 times the speed. 4 times less. And it's an oscillator. You know, it means the oscillator means the energy has to go from one side to the other side. One side makes the other side move. It's just bouncing the force back and forth. And somehow your theory is telling me that I should believe, okay, that somehow the lever changes a 1 force into a 4 force, and then turns the 4 force back into a 1 force, and it keeps doing that. It keeps converting the force into a different amount of force. I don't think it can do that. It can just convert the momentums. It can just convert the mass to velocity ratios. It can't change the amount of force that's oscillating. I really shouldn't have to argue that point over and over, but apparently I do, and that is a symptom of a real sickness here in how people function. Because even the critics should point out to this guy. I mean, even the other morons, okay, he'll say things like, entanglement is real, and photons are a wave, and but they'll concede that, yes, levers convert momentum, and they actually understand that concept, that I can convert the momentums. I mean, they should be able to, you know, make an argument somewhere in here, you know, pointing out how, you know, Ian, this is sort of bullshit. You know, you really shouldn't try to disprove that theory, because frankly that's already in conventional physics' textbook. I mean, if I go to a conventional physics textbook and show a balance, I think they're going to show it working exactly as I stated. So
it's far out on the arm. We want to test this. I don't like the idea of breaking conservation of energy. We're not unless you're going to make some money out of it.
So he's all proud of himself, okay, like he's discovered the Holy Grail-y thing or something, you know, this proof that somehow you don't have to, levers don't conserve momentum. So I think if I asked the question on a physicist survey, you know, physics won't answer these simple questions, but I think, I don't know, I did ask him a question, and he says springs don't conserve momentum, but I wonder if he's willing to say that levers don't conserve momentum, that they have to conserve the momentum. And so the only way these can oscillate at different speeds is there has to be a different amount of energy in one than the other. And I've already explained why there is a different amount of energy is because you have revealed, okay, that one of them has actually less mass. And if you did the lever right, the lever wouldn't be able to tell it's less mass. But you've made it able to tell because you're swinging the entire lever.
Was that an anomaly?
It's an error.
It doesn't look like it was an anomaly. Right, so go.
It's doing exactly as physics instructs it to do based on the configuration of the lever you've created. By having a fulcrum that's not in the center of the lever, you've destroyed the balance between the two sides of the lever and therefore broken any arguments that would be made about a proper lever, a proper balance. You've not made a proper leverage balance. Okay, it's an improper balance. It'll still work if you don't use gravity to put the force in. So I think if you actually used an external force, it would still work, because then you'd get the same amount of energy into it. So if you whack these two things on this side, the side with the double masses is the same. If you hit them, let it balance and then hit them with a force, I think you'd end up a lot closer to the same oscillation because you wouldn't be using gravity to create the force. So the same force would go into both and they'd have to conserve the momentum. But because you're using gravitational mass to initiate the action, the gravitational mass is now moving from side to side because of your broken fulcrum.
Why is that accelerating slower?
I've explained it.
Why is it frequency different?
So you can see, again, it's the whole lever is swinging on the bearing. The whole lever.
It's clear that it is, isn't it? Why is it different? Why is this one?
And the funny part is, right, is that the one with the lighter object, which they say has more kinetic energy because it's moving faster. So there's more mass moving a higher velocity as a percentage of the total. And therefore this lighter lever with the mass out here should technically have a lot more kinetic energy, right? Because its motion has a higher V. More mass is going the higher V part than mass going the slower V part. So this one should have much more energy. And ironically, this is the one moving slower. It has less energy. But whatever.
Why is this one now slower? Put the weight back. Same arrangement in both levers now. Now they accelerate together again. Back together again.
You see, he's just so pleased with himself, and obviously he's got a double fulcrum in the sense that he's moving the masses this way, the lever this way, and the lever's doing this. It's doing double motions, but clearly the real key fact is the lever can't tell the weight from the mass when it's rigid, fixed. So if you fix this center, the two sides, this side of the lever can't tell what weight is over here in terms of a mass. It can just tell what the weight is. It can't detect the mass. But as soon as you move the whole lever, the fulcrum turns. Well, now it can tell.
Nice being together. Why?
I explained it.
What is going on?
See, he's not providing. He's not providing any theory of what's going on. See, he says this little lighter object is so much harder to push. See, it has more inertia somehow. So even though inertia is associated with more mass, not less mass, he's saying it has more inertia per unit of mass. Okay, because we're going to make it go faster. So somehow it has more inertia or resistance to going faster. Now, no physicist says that. So that's not in any physics book anywhere. So he's not really arguing with me. He's arguing that regular physics needs to be changed to suit his understanding of what inertia is, and that inertia isn't mass proportional. He says it's something else. He doesn't believe what Lewin says, half the mass, twice the speed, or twice the mass, half the speed.
Slower. 1, 2, 3, go. Why is the front one accelerating slower?
Because it's less total mass on the lever, and you're oscillating the entire lever when you're supposed to be just oscillating the weights. Only the weights are supposed to be oscillating. The whole lever's not supposed to be oscillating.
It's got less weight on it.
Exactly, and you're using gravity. The initiation of the force is through a gravitational differential. And even that's an interesting subject, right? Because when the lever's in this position, it's the same pressure on both levers. Gravity's doing exactly the same thing. It's actually less, technically, there's less gravity a few inches higher. The higher you go, gravity gets weaker, it doesn't get stronger. So you haven't even explained, why does it tip? I mean, why does the object, the lighter, technically lighter object, push the technically heavier object up? I mean, technically that's how it works, right? I mean, gravity gets weaker as you go higher. So if I could make a gigantic lever, you could sort of understand that one end would be in really weak gravity and one end would be in very strong gravity, and it's pretty hard to understand how the part in the strong gravity goes up and the part in the weak gravity is able to push it down.
It's got less weight. Should go faster, you'd think.
It does go faster. It goes exactly twice as fast as the 2 mass, and the whole lever has less energy in it because you put less actual weight or mass up into the gravity, and the less mass means less momentum you put in. So the energy you put in was less. That's why it's oscillating at a slower speed. Total speed is because there's less momentum in one of the oscillators than in the other. Less force went in.
Somebody said there's more friction here, more friction on the bearings. It's further out.
I didn't say that.
There's less friction on the bearing by moving this weight out. Because there's less overall weight, less force, and it's a good bearing anyway.
That's technically it's not true in the sense that it's actually the weight of the lever. So you've been, in a sense, the fulcrum feels the weights as the same. No doubt about that, frankly.
It can't have anything to do with friction. Can't have anything to do with friction.
Everything has something to do with friction.
I don't understand it.
So you always have to watch the friction points. But anyway, so he can't understand it, and it's right there in front of us, right? He's oscillating the entire lever. So he's not putting, he's not balancing, he's not comparing two weights. He's moving the entire lever.
Same force.
Not the same force.
If I did it here, or use gravity.
Or use gravity, so you don't do that. So go ahead, hit it with a little ping hammer or something. Tap the two things with exactly the same force and see if that makes a difference. Because, technically that force you can't change. But lifting them into gravity, lifting more mass means you're lifting with more momentum. You have to use more force to lift more mass, and the more mass will fall with more force. So you put more force into the two oscillators because one of them is heavier.
get this one, to get this front lever,
it has more
same
mass.
speed,
I shouldn't
you've
say
got to apply
heavier.
more force. Gravity can't. It's a set force, isn't it? Fixed.
It's a set force dependent on your mass. So again, you can say it's a set force, but no, different masses collect different amounts of force. A heavy hammer collects a lot more force from gravity than a feather, kind of obviously. When they hit the ground, you'll see how much force the two things collected. One of them collected almost nothing. The other one collected joules and joules, watts and watts of momentum force. So it'd be kind of ridiculous to say the impact, the density of the force is the same. But if I have a smaller bucket, I'll collect less rain. I have a big bucket, I'll collect a lot of rain. Small bucket, little tiny bit of water. So what you hit with is essentially analogistic to the water. You hit with the amount of water you have. The more water you have, the more force you've collected. The less water in your bucket, the less force you collected. The feather has a tiny bucket. The hammer has a gigantic bucket. Apparently he doesn't understand that concept either.
And if we were doing it by hand, you would have to apply more force to get them to oscillate together.
No, you wouldn't. I'm sort of arguing that you wouldn't. Now, what would be interesting is if you could move this weight a little bit further out or a little bit closer in, and can you force the two things to oscillate at the same rate? Can you compensate for the mass differential that you've screwed up by oscillating the entire lever? Could you fix that by merely moving that weight a little bit further out or a little bit closer in? I would argue you could.
The force that's available won't accelerate this at the same rate as the back one. Because it's
They're what you call not in, it's like phase. They're out of phase. You could have one that has half the energy and they could oscillate at the same rate. So you could put them in phase, the same frequency rate, even though it has half the energy. So you can make them oscillate at the same rate. But what you're really changing is how high they're going. One of them will go to a higher height than the other one because one of them has more energy in it. The double seesaw you're creating here is essentially two oscillators, and you've mismatched the two oscillators. But if you actually match them so they're in phase, then you'd have the illusion that it's the same energy. But you'd have to see how high they go, and you'd notice that one of them doesn't go as high as the other.
that acceleration that creates the inertia.
So there's no inertia, okay? It's just a useless, mush, redundant word. There's just mass. Mass doesn't resist moving. You have to give it energy to move it. If it doesn't have enough energy, if you don't put enough gas in your car, I could put one drop of gas in your car, well, your car's not going to go anywhere. Okay, just not going to happen. I have to give it enough gas. I have to give it enough fuel. And that's all there is. It's nothing resists moving. You just have to give it enough fuel to move.
Thank you for watching. Comments welcome.
Yes, because there'll just be more people blowing smoke up your ignorant ass. And, so, maybe somebody will comment here somewhere where, oh, you sort of have that fulcrum way out of whack, so you got to fix that, because you're oscillating the entire lever. You're not supposed to oscillate the entire lever. So let's see if there's anything at all here. Thank you so much for doing this. It means a lot, because we need more noise experiments, because we can't keep propagandizing about this crap unless we create so many UFO pictures. Let's just inundate the world with a bunch of stupid, moronic crap so we can prove there's some validity to our wacky, silly, Jesus walks on water theory. And he says to that, thank you. Those words mean a lot to me. I mean, I need encouragement to keep making noise experiments. Keep doing things wrong and forcing somebody to explain what I did wrong. Because, gee, that sure will use up all their time, and they won't be able to do any more physics because they'll be wasting all their time, buying Barney the dinosaur suits and making videos for morons. Writing the For Double Retards book. Right? Physics for Double Retards. Alright, cool demonstration, Ian. I thought you would split the left weight to the outside too, but it's just a detail, of course. I think he means you probably should have tried it with both levers, but we'll assume it would be the same. Yes, then the distance would be more exaggerated. I don't know what that means. This was really a response to Gary. It's not balanced excuse. So he says this is a response to my it's not balanced excuse, and he takes it and he completely imbalances the entire lever. He has a moving fulcrum. Okay, so he's going to fight the it's not balanced excuse with let's move the whole frickin' fulcrum. Pretty funny and ironic. See, his other lever was using a spring, and it was only half a lever, like more lever on one side than the other side. Obvious reasons you could say, oh, this isn't going to work. Okay, you're welcome, my friend. So none of these morons could see that the entire lever was on a pendulum. Fact. Nice demo, Ian. He will still claim you used voodoo. No, you used stupidoo. Okay, his whole brain is full of stupidoo. Okay, or some other dark magic. Well, yeah, it's dark like shit. Okay, mate. Okay, thank you. Surely it's proof beyond reasonable doubt? Question mark. Proof that you people will go to any lengths to, force the truth to comply with your nonsensical, incomplete understanding of reality. And it is profoundly incomplete because you can't draw it. You can't explain how the 5-mass has more inertia. He can't explain how putting the half-mass twice the distance makes it harder to push. He can't explain that. Yes, I agree. That is proof beyond reasonable doubt, mate. So that's, it's like Professor Lewin saying the young double-slit experiment is nail-in-the-coffin evidence that light is a wave. It didn't impress Feynman, even though Feynman was a loop-de-doo and a nonsense believer. It didn't impress him. But you have to remember we are not dealing with a reasonable person. So, again, I guess that should be somebody who has an actual shit head probably can't, obviously they wouldn't be able to see who's reasonable and who's not. So that is perfectly sensible coming from a shithead. And stop calling me Shirley. LOL. Ha ha ha. Little emoticons. Funny, aren't we funny? Like the plague, you're funny. Alright. Alright. Like I can pause, right? I have the power to pause now. Alright, so this is the second video where he's attempting to say that, or defend his theory that twice the spring compression is 4 times the energy. So completely inconsistent with, again, all of conventional physics. No physicist says that I've ever seen. So he has no reference material to highlight his point. And again, he won't do drawings to explain this. Well, he has attempted in the past some, but they weren't very coherent to the subject, where he was just doing mathematical charts. He wasn't doing anything, physical. So it's a really simple experiment. Okay, you're just going to say a spring compresses a certain amount. You put a weight on it, it compresses. And the idea is that Hooke's law basically says that this amount of compression is proportional to the weight. Okay, so the mass. So twice the mass, twice the compression, 3 times the mass, 3 times the compression. Okay, it's all proportional. It's a Hooke's law. It's pretty well established. Blah blah blah. So we're going to do a simple experiment. We're just going to put a weight on a mass, and he says that somehow he's going to prove that no, twice the compression is actually 4 times the weight, so to speak. That somehow you have 4 times the energy, even though you put these units of weight are the energy, and gravity's providing the compression, with a constant force that you are collecting in a bucket, and the bucket is basically giving the weight, giving whatever water it collects to the spring in a constant manner. Now, I could do the simple analogy where you have football players, let's say, and so you have a 100-pound football player and you crash them into a spring and it'll compress at a certain amount. But if I take 2 100 football players at the same velocity, okay, velocity equals v, and crash them into the spring at the same time, it'll compress twice as much. All right. Now, if I took 1 200, say these were 100-pounders, okay, and I take 1 200-pound and I crash it into the spring, obviously exactly the same thing, okay? 2 100s, same as 1 200. It doesn't really matter if I, cut them in half and have them still run. I could slice them in half and pretend he's 2 different people. It's the same thing, okay? You can't change that fact. This is just kind of obvious. Now, I could do this experiment lots of ways. I could have a spring inside of a hole and a surface here, and I could just, roll things onto the spring to do the experiment. Or, yes, I can just lift things up and put them on. Now, somehow he thinks the lifting up thing changes something, or somehow it's important, when the lifting energy is exactly the same as any other, the gravitational thing. It's not going to change this. 2 guys aren't going to do, more lifting against gravity than 1 200-pound, right? It's just as hard to lift 2 100-pound people as it is 1 200-pound person. Same difference. So it's obviously exactly the same amount of force to do that. So there's no way to fix his analogy. So the simple point is that obviously the amount of energy it takes, to lift 2 100s. All right. So that's all we're going to do. We're going to get the spring compressed twice as much. All right, as a 1 100 person. So I lift 2 100s, and I put them on the spring. All right, it's only 2 units of energy. That's it, 1 and 2. 2 units of force. I take a 200 and I put it on the spring. Right, it's the same amount of force. It compresses at the same amount. So how could one, compress the spring 1 unit of distance, and the second one does the second unit of distance? That's exactly what will be revealed. The first one does the first half, the second one does the second half. It's 2 units. Can't be understood any other way. There's only 2 units of 100-pound energy in the spring. There's not 4 units. He says there's 4. Twice the compression equals 4 units of weight, energy, force. Of course it doesn't. I don't have to lift 4 things up to compress the spring twice as much. I only have to lift 2 things up. So I can't, I wish I could diagram it better for you, but I can't because it's so nonsensical. And again, it's not, he's not disputing me. He's disputing all of conventional physics, and yet he's directing these videos to me as if I should care. And no, I really don't. But he really thinks twice the compression of the spring is 4 times the energy of 1 compression. So the 100-pound person puts a weight on the spring. When I compress it the second amount by putting a second 100 person on, I have now 4 times that energy. How? 2 units of force, 2 units of energy. That's all it is. Can't get any more out of it.
Spring. What? I won't mean anything to you American viewers, but we had a comedian called Tommy Cooper.
Yeah, you had a lot of comedians that really weren't funny. Now, Monty Python was a little bit funny, but the rest of that shit, not funny.
And he pretended to be a magician, but everything he did, every trick he tried, it went wrong. So the cards all come out wrong, and the birds used to come out the wrong time. Used to get a lot of laughs.
You do it the opposite, so it all comes out right, but you cheat, frankly, okay, by not doing the experiment correctly.
Yeah. He used to say silly things like, you go to the doctor and he'd
How
say,
interesting.
I went to the doctor's, and the doctor said, lay on the bench. And I said, why? What's wrong? The doctor said, nothing. I want to sweep up. Anyway,
brother.
The point of the video is this business about compressing a spring and the amount of work it takes to, or energy to compress a spring. This business about if we put a weight.
So the simple argument is twice the momentum, twice the spring compression. Momentum is weight. It's that simple. It's not any more complicated than that. Whatever you put in, you get back out again. So whatever the momentum is I use to compress the spring is the total amount of momentum I can possibly get out of the spring. He says springs aren't conservative. They don't conserve momentum, that somehow they create kinetic energy. So I can compress the spring with the 10-ton train going 5 miles an hour, and I will not make a 5-ton train going 10 miles an hour. Or vice versa.
On top, or two weights, it would be less than the putting two weights on different. Putting one weight on the top down there, then another weight on down there. We got twice the compression now, 4 times the energy. I'm trying to think of a way.
Twice the compression, 4 times the energy. So he just keeps saying it. Now I'm just saying I don't think any physicists agree with him. So I don't know. Should we ask physics Michael that when I compress a spring twice as much, I've put 4 times this energy into it? I don't think that happens, and I don't think any physicists believe it happens, so I don't know exactly why he's making this arrogant, pontificating video supporting a theory. I don't know of anyone else who agrees with it.
Explaining it. It's a misunderstanding. And I'm only going to do it with one weight, and one compression. It's that simple. The first weight explains it all, without the second one.
So it obviously doesn't explain anything. He's saying he doesn't understand how gravity works. You either release the object to fall, or you don't. You can suspend it. You can hold it partially. You can do lots of things, but frankly, the entire weight is gravity. The mass doesn't weigh anything. It needs the gravity to weigh something. So all the weight, the pressure on the spring, is just a measure of the gravitational force collected by the mass. The mass can collect a certain amount of force, water. The spring's going to tell you how much water it collected.
Now, although we lift this weight up from the ground and put it on there, that squashes the spring. You could take the weight off and then let the spring do an amount of work. Okay. Why lift it from the surface? Well, it's no good having it up here. That's free energy.
No, it doesn't make any difference. It's the same gravitational force. 2 inches aren't going to change how much force is on the object, the force, the water in the bucket. So the water going into the bucket is exactly the same when the weight's here as it is on the ground. And the only difference is you've stopped. Now your hand is absorbing the water. You put it on the ground absorbs the water weight. Okay, so it's just about allowing the water weight to dissipate into something. And the spring allows the dissipation to happen over a longer period of time.
That's potential. That's like using water falling off of a cliff to drive a turbine. Wonderful. But we're talking about compression.
No, it's exactly the same. I'm just saying you can't change the weight of the water. All you're changing is the time you're allowing the weight to fall. Again, to increase its momentum, so to speak.
In a spring by lifting a weight. It's no good lifting a weight from here because it's going to finish there. The ground level.
So what? We know what it's doing while it's doing that. It's putting a pressure on the spring. And so the spring can't resist the pressure because it doesn't have any mass. It doesn't have any bucket of water on it when it's natural. You're putting the bucket of water on top of it, and now the weight has to go into the spring, the pressure. The weight hits the spring can't resist, because all it can hold up is a little tiny bit of gravity. It can only push against a little bit of gravity. It can't push against having a giant mass on the top of it. So the mass just pushes right through the inability of the spring to resist the pressure.
We'll call that. So we've got to start the lift from ground level. And I know what Gary said, that I don't need to squash the spring this whole amount. I can roll it on. I can roll it. Well, if you rolled it on from up here, it wouldn't take you any work, and it would squash the spring, yeah. But then the weight is down here.
So, what do I care? We're talking about how much energy is in the spring. How much capacity does the spring store? We're talking about the capacity of the spring. Who cares how you put the energy in? We're talking about how much energy is in there. I can't make more energy by dropping it. Moving this whole experiment a foot higher isn't going to change anything.
How are you going to get the weight back up to here to roll it on? So to analyse this properly, we've got to start from the position of lowest energy, which this is when it's, the weight is at its position.
It just amazes me. I'm just saying that he did this video on purpose somehow, and it doesn't, it says nothing.
Of lowest gravitational potential energy. To roll it off there.
So let's understand. There's no lower gravitational potential energy. Okay, you can't change how much. The whole entire time this thing is anywhere, the same gravity is hitting it. All you're changing is who's pulling the gravity out, who's sucking, okay, through friction and forcing it to stay here, because you're not allowing its weight to fall. You're forcing the weight to be suspended in a position, but the same exact force is hitting it constantly. Still weighs exactly the same. It weighs the same here, weighs the same here, weighs the same everywhere. Can't change the weight of the object. You can just use friction to stop it from moving.
That's free energy. That's potential. That's like using water falling off of a cliff to drive a turbine. Wonderful. But we're talking about compressing a spring by lifting a weight. It's no good lifting the weight from here, because it's going to finish there. The ground level, call that. So we've got to start the lift from ground level. And I know what Gary said, that I don't need to...
Yeah, what's the problem? No one said you can make free energy, so yeah, you have to lift it to get it onto the spring. The spring creates some pushing back force. You can now roll this off and put a one mass on and shoot it, and it'll restore back to half the weight. Half the spring compression, because now the spring can push the lighter mass. It can't push the heavier one.
Push the spring this whole amount. I can roll it on. I can roll it. Well, if you rolled it on from up here, wouldn't take you any work, and it would squash the spring, yeah. But then the weight is down here. How are you going to get the weight back up to here to roll it on? So to analyse this properly, we've got to start from the...
He's somehow trying to argue that it's more energy to lift it than it is to drop it, and it really isn't. It's the same amount of energy is going to be created if you lift it at the same speed. So again, we're back to the launching versus doing it slow. You could take 3 days to lift that weight to the top of the spring. Do you think you used the same energy when you took 3 days to lift it? You're going to argue you used the same calories as if you took a half a second? No, it's obviously going to be a lot less work you're going to do. A lot less. Because you're not going to be absorbing all that wet, all that water that this thing keeps collecting. You're not going to get soaking wet. The whole idea is to get less wet. The whole idea is to get less exposure to the rain. So the faster you get it to this top of this spring, the less force you'll have to absorb.
Position of lowest energy, which this is when it's,
All this position stuff, again, is baby talk, right? They should never have taught physics that this has something to do with position. It has to do with position in a stream. It has to do with how much energy is hitting the object, and it's exactly the same energy hitting the object here as it is there, as it is over there, as it is over there. No matter where I go, it's the same amount until I start going real, hundreds of meters before I'm going to change that 9.8 at all. So the 9.8 is a fixed amount. It doesn't matter where you are in the 9.8. So it's just all kind of baby talk.
The weight is at its position of lowest gravitational potential energy.
The only way you gain potential from the system is the potential to fall, to gain velocity. If it doesn't have any potential to fall, it doesn't have any potential to gain energy from the velocity it's being given, the acceleration. If you don't allow it to accelerate, it will not gain any energy. You will have to gain the energy because you will be the one absorbing its energy. So it's just about contact and electricity. You could argue that as long as you have this ground connected to the object, it can't give you, okay, all the energy just goes right through it. It can't build up its charge. But if I unground it, then it can go from 5 volts to 10 volts to 20 volts to 30 volts. It can keep increasing its voltage. But if you ground it, it can't.
Roll it off there, to get work from the spring. But now we've got to lift the weight again. And the next thing, Gary, you said, well, why such a big distance? And this is a small distance, but this is the only spring, this is the biggest spring I've got to show this distance. It all works out the same. If you was only going to compress the spring a millimetre, you'd only have to lift this weight up a millimetre. But you're still lifting it, and I'm going to...
So again, this really does have nothing to do. Again, you're not lifting at the same speed, it's falling. Moron. Okay, so if you lift it at exactly the same speed, it will compress the spring. It has to be exactly the same energy. You can't change how much energy it is. You can just do it inefficiently. The spring's going to do it efficiently. You can do it inefficiently, but you can't do it better than the spring. Too stupid.
Explain in a minute why it's important. If you only squash the spring a millimetre, you're not going to get much work out of that spring. It's not going to do a lot. And when you're dealing with such small amounts of energy...
Look, according to Hooke's law and all of the physicists and all of the evidence, it's entirely proportional. So whatever amount you compress it, that's proportional to an amount of momentum. So the numbers are completely proportional. 1 millimeter is, 1/10 of a joule. 2 millimeters, 2/10 of a joule. This kind of thing. It's completely proportional, moron. I mean, I shouldn't use joules. It's proportional to amount of foot-pound weight. Okay, the weight has to be conserved.
It's harder to analyse. It's all proportional. So the idea is to make the distance, a better distance. Then we can see. He
says it's all proportional, but his proportion is. He's saying it's twice the force in is 4 times the energy out. So how could it be proportional if you're doubling the amount of energy it has? Force. You put 2 units of force in, you get 4 units of force out. I mean, that's what you're saying, and it's irrational. Sorry, it's irrational.
Analyse what's going on. I'd rather have a foot-long spring. That would show it better what I'm talking about. Because you're not going to get much work out of a spring that only moves. What can you do?
There's absolutely no way he can rationalize this. I'm just still going to say that the person doing it can make this spring compress 1 amount by just lifting 1 ounce, and it compresses 1 ounce worth. And then he can compress it 2 ounces by just lifting 1 more ounce, 1 more amount of force. He puts it up there, he drops it, it's compressed twice as much. There isn't 4 times the energy in the spring, and clearly the spring can't even lift up the 2 ounces. That's why it's stretching, or that's why it's compressing, is because it can't hold it. It can't push against it. It doesn't have the energy to push against it. It only has 2 ounces worth of energy. It only has 2 ounces worth of counterforce. How could it possibly have 4 ounces of counterforce? If it had 4 ounces of counterforce, it would push the object back up. It has to have exactly the same amount of force to stay in that condition. The 2 forces have equalized. I mean, damn.
Squashing a spring about a foot, and then letting the spring expand and driving a piston. Pushing a push rod and then a crank and moving a flywheel. So we can analyse that level of energy. But it's all relative.
Why would he say that? It's all relative. Why would he say you could do all that stuff? You can only get back what you put in. 2 units of force in, 2 units of force out. That's all you're going to get.
It's all completely relative.
No
So we're going to
relative.
use this little distance to explain it. Right. Here we go.
You have to understand the difference between a constant force and an impulse force, right? So if I hit something with an impulse force, it only has that ability to push once, and that's it. The constant force is basically saying the force will keep on coming. It'll keep pushing and keep pushing and keep pushing. So there's no point where it hits and then you give back the energy, because it keeps adding energy every millisecond. Every millisecond, the same amount of force is leaking into the spring. So the spring can never give back the energy because you keep pushing new energy into it. And the ground is now absorbing the extra energy is now going into the ground. The first bit of energy the spring absorbed. The second piece of energy the ground is absorbing.
This is it. This is the key. I've got to lift this weight. As soon as I start lifting it, the force I'm using is the weight of this weight. Say it's a pound.
It's not the weight, it's the weight per unit of time. Per unit of time, the weight is added and added and added. So it's a constant force, and the more time you move it, the more force you're absorbing.
Right? So it's a pound. I'm putting a force of a pound at 1 millimetre. I'm putting a force at a pound at 2 millimetres. Every increment of distance.
So again, it's just absolute nonsense, right? Because if we lift it at exactly the speed it pushes out, then we will use exactly the same amount of energy the spring produces. But if I lift it slower, I'm going to do a lot more work. So again, he's not getting it, that if I extend this period of slowness that he's lifting it, and I make it slower and slower and slower, you're going to do more and more work. You're going to absorb more and more force. You're fighting more and more force. So if you do, the quicker you do it, the less force you'll actually have to use to get it to the location. And there's a perfectly efficient speed. You know, where you're not going so fast you'd go too high. So you want to go just fast enough where it stops at the right height. And if you do that, it'll be exactly the same force you'll get back.
I'm having to use a pound of force up to the height. Try it on. You got that? All times it's uniform, the force I'm applying.
Yeah, and it's adding up. The longer you take to lift it, the more the force adds up and the more force you're used. So you can do it really inefficiently or you can do it really efficiently. So if you launch it to its location, essentially, at the higher velocity, you move it at the higher velocity, you will gain a huge efficiency in how much energy you'll use to lift the object. So again, he doesn't even get this basic theory.
Of 1 pound. That whole distance. And they say, you know, work is force times distance. 1 pound.
That's as far as I listened, right? I mean, there's little key moments where you just say, okay, but you're still not getting it. Obviously, they say that, and they say it irrationally, because the force isn't proportional to the distance, it's proportional to the time, especially in gravity. It's all about how long, okay, you're resisting the force, not how much distance you travel. How much distance you travel will be an emergent function of time. But the actual thing that's deciding how much energy you're using is not the distance. That proportionality breaks down. The higher your velocity, the more distance you cover in less and less time. Obviously, the time factor is the only factor creating the force. The force is entirely a function of time.
Over that distance. Never mind about in steps, incrementals, fast, quick. 1 pound of force constantly, isn't it? Up to that height. Anybody can see that.
Constantly for an amount of time. I mean, again, he just keeps breaking the simple rule. It's an amount of time. It's not a constant force for the distance. It's a constant force for the time you're in it, resisting it. With the time you're holding it, you can have it on the ground, and the ground's got the problem. And the ground will feel the pressure constantly. You grab it, now you're taking responsibility. Now it has to go through you, and you're going to have to use energy to keep moving it. Ugh, brother, it's just too stupid. Holding it against gravity, and there's an illusion. You're not holding it against gravity. You can't hold it in one position because it's bouncing. You're going to have to compensate for that.
Constant. That is going to take more energy for me to do that than if I get my finger and...
So it means this means nothing. I mean, he's still saying there's 4 times the energy in twice the compression, which is ludicrous nonsense. I mean, there's no way this proves there's 4 times energy in twice the compression. It's nonsense.
And compress the spring manually. What?
And again, you're doing it at a speed, which means the pressure now that the spring, you're overcoming, you're creating more than the gravitational force on the spring, in the sense that you've added an extra mass, plus given that mass an extra velocity. So you're pushing down with a weight, okay? And it's more weight in some respects than the weight you had suspended, in the sense that it's more weight per unit of time. And that's why the spring is compressing. And you can compress it. The weight compressed it quickly because the weight has more weight per time. You're doing it slower than that. So what?
Why? Because as I start compressing the spring, there's not 1 pound of force necessary. There's hardly nothing.
It's exactly that. So that's the nonsense. Of course, it's 1 pound, 2 pounds, 3 pounds, 4 pounds. Let's say the total thing was 4 pounds. Twice the compression will be, compressed to half its size will be 2 pounds. The spring has been proven to be linear with weight. So how can you say this crap?
Millimeters is a gradual bit of resistance. I might have 1/10 of a pound force necessary. And then as I get a bit more, that force is gradually increasing. Right,
and it's exactly proportional. 1 pound gets you this, 2 pounds gets you that. 2 pounds is twice as much the compression. So I don't understand how he could possibly make a video saying Hooke's law is nonsense. How can he say that with this crappy experiment? I mean, something so well established by physicists. That experiment's been done hundreds and hundreds of times, putting the 1 mass on, then putting the 2 mass on, getting twice the expansion of the spring. I mean, that's been proven over and over and over again. Why would you make an argument against it? I mean, it's just silly.
Halfway, it's about 1/2 pound of force. Until I go right up till full compression, where I'm only now using 1 pound of force. So you could say the average force used about halfway, 1/2 pound of force, say.
It's absolute nonsense, because again, you're applying the force in a constant manner. So you're not applying an impulse amount of energy and then having the spring produce the energy back. You're forcing the spring to stay compressed by adding a constant force. So I guess you really don't get the whole constant versus impulse. There's no real difference. I mean, it's the same weight. It's just a matter of the durability of the weight. Is the weight durable? Does the weight continue to weigh? The football player running into the blocking dummy, he can continue to push, but obviously, in most cases, the impulse is the one that's going to do the work.
So by doing it by hand, the work I've done is 1/2 pound times the distance. It's about half the work than if I've lifted this.
All right, so it's just too silly. It's half the work. He's saying he can feel it's half the work somehow. So creating the 1 pound of pressure, now that didn't even make sense, right? Yeah, that would be half the work. I don't know what he's saying. It's too silly. That's all I know is he's saying that somehow I do half the work and I get twice the work back. I get a full work back. No, you don't.
Weight up, which is 1 pound for the whole distance. Double the work.
Okay, so again, he keeps saying that it's double the work, when obviously, depending on the speed you lift it with, it's more work. If I lift 100 pounds really slowly, I'm going to do more work. There's no doubt about it. The 100 pounds is in the gravity for a longer period of time, and I'm the only thing able to fight those seconds and seconds and seconds of gravitational energy. The gravitational energy is coming in units of time. It's just, I don't believe I have to argue in defense of something so fucking obviously true.
To plonk this on than it is to press it down by hand.
Oh, what a pile of crap. So he's saying he doesn't have to use the same amount of force to compress the spring, when of course it just depends on how long you decide to take to compress the spring will decide how much energy you're using. It's just about time, because gravity is time dependent, and clearly your use of force will also have a time dependency on it. The longer you have to fight something, the more energy you're going to lose.
Can you see that?
No
We
way.
haven't got to worry about the next way. That is telling you why that free energy nonsense is wrong there.
There's no free energy nonsense, okay? The simple argument is 2 units of force cannot equal 4 units of energy out. 2 units of force in, 2 units of force out. You cannot do whatever it is you're doing. This twice the energy for twice the compression of a spring is a nonsensical theory. You just can't say that without proving it some way, and you're not proving it in any way whatsoever.
I hope you can understand that. On to the next one.
Yeah, the next one is the silly lever pendulum thing. So, all right, let's see if anybody says anything here to point out how you're saying Hooke's law isn't a law. Gee, that's kind of stupid. Remember, it doesn't matter how small a lift we do. The resulting stored energy of the spring is proportionally reduced in the smaller compression. Proportional meaning what? 1 to 1? Same force, 1 unit of force, 1 unit of energy. You can't cheat nature and the conservation of energy, Gary. So he's using sort of a, Professor Lewin statement. So instead of disagreeing with Professor Lewin, he's disagreeing with me, which is kind of silly. I'm defending conventional physics in this case, and he's attacking it. They believe you have to conserve the momentum, and that springs do in fact store momentum. That's what most of the physicists believe. But anyway, I love the story about Tommy. Oh, god damn it. Saying, okay, so he's just did his joke thing, so never mind. Yeah, the average force seems to be the correct value. So, what does that mean? The average force is always the same. If I'm lifting 100 pounds, the average force is 100 pounds I'm fighting. And all I can do is collect more 100. I can go slower and slower and slower and make the weight add up over time. I can take more and more time to force against the force, the constant force. I can just create more constant force I have to account for by taking longer to lift it. Because of the object can gain velocity, thus has energy. So again, it's absolute nonsense to make this argument that you're not allowing it to gain velocity. That's the whole point of him lifting it the same distance in the same time. He's telling us basically he's not going to take advantage of the acceleration increases, the advantage of increasing the velocity and shortening the amount of time the object's in the gravity, which means it can bypass the 1 pound of force. So this is just such drivel. That means the work used to go up is equal to the work applied by the spring. So it never will be unless you lift at exactly the same speed the spring compressed or the spring expands. If you do it at some other speed, it will not be the same work. So you're just wrong. In this case, the spring can't compress any further, so the work would go into producing mostly heat. well, what it's producing is the Earth pushing back. You know, it's not just, you could call that heat, but it's really a little more complicated than that. You're you're deforming the Earth. You're pushing into it. It has to push you back. Okay, that means a whole bunch of stuff has to move to do that. You have to increase the pressure on the Earth, the total pressure the Earth has. And by increasing it, you've created its capacity to push back. Basically, even though the force used to go up is constantly higher, so what does that even mean, right? He thinks that the higher you go, you change how much gravity you're in. When no, the higher you go, the less gravity you're in. So he doesn't get that part right. Then the force used to go down, whatever that means. This force the force moving down, you're going upstream. The force that can push you downstream is exactly the same as the force you have to push against to go upstream. It makes absolutely no difference. It's the same exact force. The stream has a force. That's all there is the force of the water. The work is the same in the downward force, also has velocity. So somewhere in that paragraph he's agreeing that's twice the compression of a spring, 4 times the energy. Which again, I'm just saying is obviously a nonsense. I just wanted to help anyone understand why Gary's claim he could get double the work out of the spring by lifting 2 weights onto the spring to compress it is wrong. I didn't say you get double the work. I'm saying that I can create 2 pounds of pressure by putting 2 1-pound objects on a spring. I can compress the spring twice as much by just doubling the same exact amount of force. I can add 2 units of force and get 2 units of compression. You're saying the 2 units of compression are 4 units of energy. I'm saying that's crazy. Wow. You really can't stay anywhere near the subject. Do you think I managed it? Question mark. I think it will convince most people who are interested in the topic. So what are they going to be convinced of? I'm sorry, what possible conclusion could you draw from that incoherent pile of slop? He didn't even overtly say, look, twice the compression is 4 times the energy. I mean, he didn't even say that. But you really think you can convince people that that experiment proved it? The physics in general, but new viewers may be a bit confused. I think the longer spring would help. How would it help any? He's saying twice the weight is 4 times the weight. When is that ever going to be reasonable to anyone? But somehow you people are falling for it. Thanks. Yes, if you don't watch DraftScience, then and what he claims, you've got no chance. What is this? Thanks. Yes, if you don't watch DraftScience and what he claims, you've got no chance. I don't know what that means. So Stephen Bro, another look at him. He's resorting to 3-word. You know, he used to paragraph after paragraph, and now it's just this crap, just like that. I don't know what that means. You killed Zibididi. Huh. What the fuck? Another joke Americans won't get. Yeah, that's right. I don't even want to get near it. Woof. Let's see. I just get depressed realizing all we have come down to is Gary's level of unreasoning. What? So they claim twice the compression of a spring is 4 times the energy is now in the spring, and sometime it can do 4 times the work somehow. When it can't. I don't know. I mean, it's just too stupid. He's saying it takes twice as much energy to compress the spring the second amount. So I compress it 1 amount. He says it takes twice as much energy to compress it the second amount. No, I just add another person. I just put another person on the spring and it's compressed twice as much. I mean, how can anyone argue with this? Let's see, but yeah, the magic roundabout was okay. So he's just going to talk about his little stories. He watches his little stories on TV. Usually MGH. So again, they're still saying it's the same force. It's just the distance that matters. So walking really slow over a fire is the same as walking really fast over a fire. You'll get burned just as much. You get burned just as much. Doesn't matter how fast you walk across the fire. Can't link. So here's the description. Lecture de Puba Papa Puba of Spring Expansion and Power of Spring Bodies, Robert Hooke. So he's saying that somehow what this guy is arguing is a defense of Robert Hooke. I mean, the joke here is that Robert Hooke basically, stated that twice the compression is twice the weight, and that's all you got, 2 units of force. Perfectly proportional. 2 pounds is twice as much as 1 pound. It's not 4 times as much. I don't know what. Alright, so there's nothing else to say. This is just so irrational. Oh, God. Alright, anyway. So enough of a video and such. Yeah, more than enough. So, till the next time, I just, yeah, what's the point? It's just becoming clear. I mean, people are either too dishonest, like Physics Michael is dishonest. I mean, he's basically claiming I'm not making any counter arguments that are worth his time. So he doesn't have to explain that gravity isn't a time-dependent force. He doesn't have to counter my argument that it's a completely time-dependent force. I mean, it's pathetic. Scummy liars are way too stupid fucktards. That's all that's on the fucking planet. Scummy liars and way too stupid fucktards.